Hi, this is a report on the design of the clock module for the Tangerine SDR. Tangerine SDR requires a couple of different clock frequencies. The most important one is probably the 122.88 megahertz that drives the RF modules, but there's also a pulse per second along with timestamps that are used for data tagging, and we'd like to have a 10 megahertz general purpose reference signal available. Those signals will all be generated by a GPS disciplined oscillator. In addition, the GPS module will allow us to generate a measurement called a total electron count, which is something that the science community would like. So we'll make that data available to the data engine as well. The GPS-DO specifications are a little bit hard to pin down because the science applications are so broad, but after talking with the teams, I think that the following specs will more than meet the requirements for all the science experiments that are currently contemplated for the Tangerine SDR. And that's a frequency accuracy of better than 1 part in 10 to the 12th, or a part per trillion, a frequency stability in the short term of better than 1 part in 10 to the 9th, or 1 part per billion at any tau or averaging interval from 1 second or greater. The absolute PPS time accuracy will be within 100 nanoseconds of UTC as realized by the US Naval Observatory, and the jitter on the PPS signal will be less than 10 nanoseconds. Because this is an RF application, phase noise of the 122.88 megahertz is important, and our target there is better than minus 80 dBc at 100 hertz offset, and better than minus 150 dBc at 100 kilohertz offset. As I mentioned in my previous presentation, a GPS-DO is really a way to get the best of both worlds of using the better short-term stability of a crystal oscillator and the long-term accuracy and stability of the GPS constellation. The magic is to use a PLL, a phase lock loop, with a time constant that allows the crystal oscillator to dominate in the short term, filtering out the noise of the GPS signal, which takes over in the long term. This plot, which I shamelessly stole from the SRS company's website, shows a GPS-DO model for a little bit different environment. They're using a rubidium frequency standard, which is much better in terms of short-term performance than the crystal oscillators we're using. But the plot clearly shows how this all works. Here we have the GPS pulse per second signal at the black line, and you can see it's quite bad at short term. It keeps getting better and better and better. The red line is the rubidium standards raw output, and you see it's quite good, and it stays quite good for a long time, but ultimately it starts to become worse than GPS out here near the right of the plot. With a properly designed phase lock loop, we'll get this blue line where we get the short-term performance, but then we transition to the long-term of GPS. Now, we lose a little bit of this transition interval, but that still isn't bad, and it gives us a single source that has the best of the short-term and the long-term performance. And that's what we're trying to accomplish in the Tangerine SDR clock module. So to take advantage of the performance improvements that we get by using the dual frequency receiver, we can look at the previous chart and sort of redesign it. Since our noise after dual frequency plus sawtooth correction is down around 5 and 10 to the minus 10th. That's actually better than our short-term spec. We don't need a long time constant. We can use just a few seconds. And that allows us to use an oscillator that doesn't have long-term performance that's as good. And that means that's a cheaper, lower cost oscillator. And we can spend that money instead on the more expensive GPS module. So we may not save money overall, but we're transitioning where we're spending the money to be able to get other features. This Allen deviation plot kind of shows the tail. The green trace is the performance of a crystal oscillator that's very similar to the one that we'll be using. And you can see that its best performance occurs at around 1 second right in here, but it starts to go up fairly rapidly because of temperature and aging and other factors. This blue line is a traditional GPS, and we can see that the point where they cross over is out here at about 25 seconds, and the Allen deviation at that point is about 2 and 10 to the minus 9th. and that's not quite as good as we would like our system to be. However, if we switch over and use the ZF9T PPS, which is the magenta line, now the intercept point is at about 2.5 seconds, and the worst case Allen deviation is about 2 and 10 to the minus 10th. So we've picked up an order of magnitude in performance, and now we can generate a signal that is actually quite a bit better than the specification, which is a good thing because we'll never quite achieve this absolute crossover in practice. The noise hump at the transition will probably be just a little bit higher. So this design should let us meet our design spec using a direct control of the 122.88 megahertz TCXO. And that means we don't need a 10 megahertz oscillator in the mix either, which is another cost that we can reduce. So the key design points of the GPSDO are, again, to use the low PPS noise to allow a short time constant. We'll phase lock the 122.88 TCXO directly to GPS. There won't be a 10 megahertz crystal oscillator. However, we'll make a 10 megahertz output available by synthesizing it in the FPGA. And speaking of that, the FPGA will serve as both the connection matrix and the processor for the clock module. Pretty much everything goes through it. And the reason for that is to allow us to reconfigure the system quite easily without having to move a lot of hardware around. The board will allow lots of extra I/O to allow different implementations. So for example, we could use a 10 megahertz crystal oscillator as our disciplined source. And then we could also generate 122.88 with a low noise synthesizer chip from that 10 megahertz. Or alternatively, we could keep the 122.88 megahertz oscillator, but instead of locking it to GPS, we could lock it to an external 10 megahertz source, like a local frequency standard. So we'll have the capability to implement the GPSDO in different ways. And it's also important that the module can be used independently of TangerineSDR. We'll have some sort of an adapter to allow it to mount, for example, on a Raspberry Pi and serve as a standalone system. And of course, the hardware and the firmware are all open source. This is a block diagram of the clock module, and it's probably impossible to read, so I won't try to go through its details. But the key takeaway is that pretty much everything goes through the FPGA, which is this block here. And that again allows us the flexibility to reroute signals and to try different implementations. The output is here, the 122.88 megahertz oscillator, which drives a four-way buffer and provides the four output signals that are needed by the RF modules. And then we also have other signals that go directly from the FPGA to the output connector, which is this block. So at this point, we have the block diagram finished. We're starting to think about turning it into a schematic and then a board layout. But now that we've tested the GPS units and we know how they work, we're very confident that this design will give us a clock module for the TangerineSDR that not only meets the requirements, but provides in itself a test bed for further experimentation. So thanks much.